The Strange Black Hole Part 2. Initially, when astronomers observed this gravitationally lensed galaxy in a Chandra X-ray image, they were uncertain about its nature. They investigated 11 similar gravitationally lensed galaxies detected by Webb and identified an X-ray source that matched their target in terms of position and X-ray spectral characteristics. This X-ray source, amplified by the cluster lens Abell 2744, was eventually identified as belonging to the galaxy UHZ-1. These X-ray images from the Chandra telescope played a crucial role in identifying and studying the gravitationally lensed galaxy UHZ-1. The first image showcases the massive cluster lens, Abell 2744, with a small square box highlighting the location of UHZ-1, which harbors the massive black hole. The next image reveals the extent of X-ray emissions from the galaxy and its vicinity. In this image, a pale yellow indicates high X-ray counts, while black represents the lowest counts. The central region, where UHZ-1 is situated, showed the most intense X-ray emission. After analyzing the X-ray spectral properties of the accreting black hole at the center of UHZ-1, astronomers estimated the black hole's mass to be between 10 million and 100 million times that of the Sun. But things took an interesting turn when they calculated the galaxy's stellar mass by analyzing its starlight emissions. That number came out to be roughly the same as the black hole mass. This contrasts sharply with observations in the local universe. For example, the black hole at the center of the Milky Way constitutes less than 0.1% of the Milky Way's stellar mass. This was the first time astronomers discovered a galaxy whose stellar mass and black hole's mass were comparable. The only thing now left to find out was how this supermassive black hole possibly formed in the first place. To determine whether the black hole in UHZ-1 originated from a light seed or a heavy seed, scientists developed two models and conducted simulations to observe how these seeds would evolve if they originated around 150 million years after the Big Bang. The key question was whether they could attain the estimated mass by the time the universe was about 500 million years old. In the first model, a light seed arising from the remnants of the first stars began with an initial mass of 10 to 100 solar masses. It evolved by accreting matter at a rate consistent with the Eddington limit. However, the simulations showed that such a light seed would fail to reach the estimated mass of around 100 million solar masses. Conversely, the second model involved a heavy seed starting with an initial mass between 10,000 and 100,000 solar masses. With consistent accretion at the Eddington rate, this model successfully reached the required mass estimate. Additionally, scientists explored a third scenario, where a light seed accretes matter at more than twice the Eddington rate. This model would necessitate an enormous amount of matter being fed to the black hole over an extended period of about 300 million years. However, this scenario is considered highly improbable, as it requires a sustained supply of gas to the black hole even after the matter has lost all angular momentum. This situation is unlikely, given the dynamics of such systems. There are 4 reasons why this study is important. Firstly, it supports the heavy seed theory, suggesting that such early massive black holes originate from the direct collapse of vast gas clouds. Secondly, the galaxy hosting this black hole presents a unique case where its stellar mass is approximately equal to the mass of its black hole. This categorizes it as the first ever outsized black hole galaxy, or an OBHG, a rare phase in galaxy evolution where a heavy seed is present. This phase lasts until a transition occurs, flipping the mass ratios to those comparable to the local universe. Third, the study highlights the importance of gravitational lensing yet again. Gravitational lensing has enabled us to discover this unique black hole and even Earendel, the most distant single star identified to date. Lastly, considering the universe's age of around 13.7 billion years, the identification of a black hole in UHZ-1 dating back to when the universe was only 470 million years old positions it as the earliest black hole ever discovered. Follow Arrowway for more such content.